السلام عليكم. السلام عليكم ورحمة الله وبركاته. كيف الحال يا شباب؟ إن شاء الله تكونوا بكل خير. Today we continue our recorded lecture and we finish what we have started last week about the different kinds of vector multiplications. So we mentioned we came across four basic types of vector multiplications, which were the first one was the scalar product or the dot product. Number two, it was the cross product. Number three, it was the triple scalar product. And number four, we had the vector triple product, and we defined how to calculate each one of them. Okay. And in the last lecture, we have started a long example actually, and we had done some of the requested questions, and I think we reached to part D. Okay, part D, which was asking. So we had three vector fields, P, Q, and R, and we got to point D, where it asks for the sign of the angle between vectors Q and R. I think we did that part. Now let's move to part E, which asks for the vector triple product between the three vectors P, Q, P cross Q cross R. Okay, so let's go to the whiteboard. Allahu Akbar, Allahu Akbar. And let's finish the example here. So we have vector P. أشهد أن محمد رسول الله. 2 minus 3 1 2 1. Yes. So we need to find the vector triple product by using the back minus cab rule. So this is A. Let's say this is A, B, C. We have cab minus. So sorry, we have back minus cab. Okay, so we have B is Q here, so we have Q Allahu Akbar, Allahu Akbar. P dot R minus C is R. Allahu Akbar, Allahu Akbar. A, B, P, Q. Okay, this is how we find the vector triple product. Okay, now first we need to find the dot products, P dot R and P dot Q. So P dot R is equal to what? P and R, we have 2 times 2 minus 0 plus our minus 1. Okay, so it's 4 minus 1, which is equal to 3. And we have P dot Q is equal to what? 4 minus 0 minus 2, which is equal to 2. Okay, so we have this equation is simplified to be 3 times vector Q minus 2 times vector R. Okay, so 3 times vector Q is 3 times 2a sub x minus ay plus 2az minus 2 times vector R, which is 2a sub x minus 3a sub y plus a sub z. Okay, this becomes 6a sub x minus 3a sub y plus 6a sub z minus 4a sub x plus 6a sub y minus 2a sub z. Okay, now we collect each components in the same direction together. So we have 6a sub x minus 4a sub x. So 6 minus 4 in the x direction, plus we have minus 3 plus 6 a sub y, and we have 6 and minus 2 in the z direction. Okay, this becomes 2a sub x plus 3a sub y plus 4a sub z. Okay, so this is the end result for the vector triple product of P, Q, and R. Okay, let's see what else we have. Okay. Part F is asking for a unit vector perpendicular to both Q and R. So we want to find a unit vector that is perpendicular to both Q and R. Okay, so to find this unit vector, we need to do 2 things. First, this is a vector, so it has a magnitude and a direction. This unit vector, it has a magnitude of unity, and the direction should be perpendicular to both Q and R. So it has this vector, it has to be with in a 90 degrees angle with both Q and R. Okay, so let's think how we get this vector. First, let's think how we get this direction, a vector to be perpendicular to both Q and R. The magnitude thing is easy. Whatever vector you get, you divide that vector by its magnitude, you get a unity vector. But the most important thing here is the direction. So we want to find a vector. Let's call that vector C. We want C to be perpendicular to Q, and we want it to be perpendicular to R at the same time. Okay, so from where we get this vector C? This vector C could be obtained from where? It's okay. Okay, this vector C could be obtained from where? It could be obtained from this relation. If we say C is equal to the cross product between Q and R, then we said the cross product between Q and R should give us a vector that is perpendicular to both Q and R and the whole plane containing Q and R. So let's say if we have, this is vector Q and this is vector R, for example, if we do the cross product between them, then the resulting vector will be a vector that is directing in a direction that is perpendicular to the plane containing Q and R. Okay, so this is from where we can get such a vector. Let's see, let's say this is C. Okay, this is R. Okay, so this is the first thing of, you know, solving out this question. So it asks for a magnitude of unity and a direction that is perpendicular to Q and R. So we started the direction by saying that C is equal to the cross product between Q and R. Okay, how do we perform the cross product? We put the unit vectors first, A sub X, A sub Y, and A sub Z. And then the components of the first vector, which are 2, -1, and 2. Then the components of R, 2, -3, and 1. Okay, and we find the determinant of this. So it's like A sub X -1 plus 6 minus A sub Y 2 minus 4 plus A sub Z. We have -6 plus 2. Okay, so it's equal to 5 A sub X plus 2 A sub Y minus 4 A sub Z. Okay, so this is vector C, which, you know, satisfies the first requirement of the question, which is the direction of C is perpendicular to Q and R. Now we have achieved the first requirement of direction. Now we move to the second requirement of magnitude. The magnitude of C should be unity. So how do we find a unity vector from C that's at the same direction of C? It's the unit vector that directs in the same direction of C. So we call it A sub C is equal to what? To C divided by its magnitude, okay, which is equal to 5, 2 minus 4 divided by what? 25 plus 4 plus 16. And we take the square root to this quantity. This is going to be 29, 39. Okay, square root of 45. So it's the square root of 45 multiplied by the vector C, which is 5 A sub X plus 2 A sub Y minus 4 A sub Z. Okay, so this unit vector A sub C is the answer for part F. It's a unit vector. It has a magnitude of 1, and its direction is perpendicular to both Q and R. Okay, and if you want to make sure that your result is correct and that A sub C is really perpendicular to Q and R, you can perform a cross product between A sub C and the Q, and the you can perform a dot product between A sub C and the Q, and the dot product should give you 0. And you can have a dot product between A sub C and R, and it has to have a result of 0 as well. So to check your result, you can have A sub C dot Q, it should give you 0. And you have to, you do A sub C dot R, it has to have a result of 0 as well, because if the angle between the unit vector and the Q is 90, then the dot product should be 0. And if the angle between A sub C and R is a 90 degrees, then the result should be 0 as well. Okay, let's get back to the notes. Part G, the component of P along the Q. Okay, let's do this later, because I have to talk about the section that is about the component of a vector along another vector. So we do this after I talk about this section, the coming section. Okay. Okay, section 1.8. So let's talk about section 0.8, and then we do part G of the previous example. So components of a vector. Okay, let's say, let's go to the whiteboard, and let's have two vectors. First vector, let's call it A. This is vector A, and the other vector should be, we call it like B. Okay, this is vector B. Okay, we can, for any vector, let's say vector A, for any vector, we can have a component of vector A along vector B, okay? Or we call it the projection of vector A along vector B. So we call it, or we represent it using this symbol. So we have A along B. So this means the vector components or the vector projection of A along B. Okay, and we can have another notation, which is A sub B. It is the scalar component or projection, scalar projection of vector A along vector B. Okay, so any vector could have a projection onto another vector. Okay, this projection could be a vector projection or a scalar projection. Let's start with the scalar projection. So with this example, with these two vectors A and B, let's find the scalar projection of A along B. A sub B. Okay, A sub B should be equal to the vector A dot the vector B divided by what? By the magnitude of vector B. Okay, this should give me the scalar projection of A along B. scalar projection of A along B or onto B. Onto vector B. Now, if we can write this equation in another way. We can write it like this: A dot B divided by its magnitude. Okay, and B divided by its magnitude, we can replace it by what? We can replace it by the unit vector along B. So A dot the unit vector along B. So these are three equations that are equivalent to each other, and all of them give us the scalar projection of vector A onto vector B. Okay, so the end result here is a scalar quantity. Okay, now let's move to the other part, which is the vector projection of A along B, which is, we notate it like this: A sub B, and we indicate that it's a vector. So the vector projection of A along B is equal to what? Is equal to A dot B divided by the magnitude of B. Up to this point, we have a scalar quantity. Okay, this is a scalar quantity. So the other side of the equation, this one, is a vector quantity. So we have, this is the magnitude of the projection. This is the magnitude. We need to give this magnitude a direction, so the equation will be balanced, okay? Because the left side of the equation is a vector quantity, the right-hand side is a magnitude quantity. If we add a direction to the right-hand side, then the equation will be correct. So which direction now should I give to the right-hand side of this equation? We said that the right-hand side represents the projection or the vector component of A along B. So along B means the direction. So the direction I give to this magnitude should be a unit vector along the vector B. Okay, and this way the equation is totally correct. Okay, so we have a vector projection of A along B is this scalar quantity multiplied by a unit vector along B. If we compare, let's say this is equation number 1 and this is equation number 2. If we compare the two, we see that they both have the same magnitude, but equation 2 has an extra piece of information, which is the direction. Okay, we can simplify this equation 2, to be like this: A dot B divided by its magnitude. Okay, and we give it a direction, and then we can say that B divided by its magnitude is a unit vector, so A dot AB multiplied by a unit vector. Okay. Okay, let's see how we can perform this graphically. Okay, so this is vector A. The scalar component of A onto B is a straight piece. Okay, that is, its magnitude is equal to AB. Okay, it's not a vector, it's just a straight piece having a distance of A sub B. Okay. It's like this. It doesn't have to be to finish the whole length of B. It could be, it's just a projection of A. Okay, like this. So this is A sub B. which is a scalar quantity. Okay, now if we want to find A sub B, the vector projection, it should be something that having the same magnitude as the scalar quantity, but with a direction. So this one should be like this. So this is the vector projection of A along B. So in terms of magnitude, it's the same as the scalar one, but we add this arrow to give this projection a direction along B. Okay, so this is vector A, and this is the okay. So this is vector A, and this is its projection along B. We call it the vector projection. We call it A sub B. Okay. Now the vector A could be written in terms of two components. Okay. The first component is its projection along any other vector, which is vector B, plus the other component which we call it A perpendicular to B. Okay, so any vector A could be represented or analyzed into two components, two major components. The first component is the projection on another vector B, and the other component is the component that is perpendicular to vector B. Okay. So, okay, so let's say I have a question for you, and I give you the vector A, and I give you the vector B, and I ask you to find the vector vector from A to B, and that vector is perpendicular to B. Okay, I ask you to find a vector that connects B to A, and that vector is perpendicular to vector B. Okay, so you can first find the projection of A along B, which is this projection, and then you say that the perpendicular vector A perpendicular to B should be equal to what? Should be equal to the vector A minus its projection onto vector B. Okay, let's get back to the notes and see if we have covered everything. So we said that the scalar product or the scalar component of vector A onto B could be written in this way, okay? Or we can write it this way. The magnitude of, this is the magnitude of A times the magnitude of the unit vector, which is 1, times the angle, cosine the angle of that's between the two vectors, which gives us this formula. So the scalar product, the scalar projection of A onto B, it could be A dot the unit vector along B, or it's the same as saying it's A cosine the angle between A and B. And for the vector projection of A along B is the same as, its magnitude is the same as the scalar projection, but we add a unit vector here along B to give the scalar quantity a direction. Okay. Now, here in this graph, we see this is the vector A. And if we want to find its scalar projection onto B, we have this projection. So this is A sub B as a distance, as a straight a straight line. Okay, but if we want to find the vector projection of A along B, so this is A again, and the vector projection is this vector from A along B, and it has this direction, this arrow, to indicate that this is a vector and it has a direction. And this perpendicular piece, or this perpendicular vector from B to A, represents A minus A sub B. Okay, okay, let's get back to the example, to the long example where we stopped at part G. Okay, so we had 3 vectors, P, Q, and R. Okay, and the last requirement in this example is part G, which asks for the component of P along Q. Component of P along Q. Let's get back to the previous slide. Okay, so let's delete this thing. Okay, so part G asks for the component of, let's make sure, component of P along Q. Of P along Q. Okay, here in this, in the question statement is not, it's not telling us whether they want, you know, a vector component of P along Q or a scalar component of P along Q. If it was a question in the exam, I will specify for you which kind of component I want, whether it is a vector component or a scalar component. But for this, let's do both of them. Okay, start with the scalar component of P along Q. Okay, so we use this notation, P sub Q. Okay, P sub Q should equal to what? Should equal P dot Q divided by its magnitude, which is equal to P dot A sub Q. Okay. Now P is equal to what? 2 A sub X minus A sub Z. We perform the dot product with Q. 2A sub X minus A sub Y plus 2A sub Z. Okay, and then we divide by the magnitude of Q, which is 4 plus 1 plus 4, which is the square root of 9. So the dot product, performing the dot product, let's put the factor of 1/3 here, and then we do the dot product. So we have 2 times 2 is equal to 4. The Y component here is 0. So it's 0 in the dot product, and then we have minus 1 times 2, which is minus 2. So the dot product will be 2/3. Okay, so this is the scalar component of P onto vector Q. Now we want to find the vector component of P along Q. We have the magnitude already, which is 2/3. We put it here, and then we give this vector a direction. The direction should be along what? Should be along Q. So we just add a unit vector along Q. Okay, and this is the yeah. So for A sub Q, we have to find A sub Q first. A sub Q is equal to what? Q divided by its magnitude, which is equal to this thing, which is 1/3 times 2a sub x minus a sub y plus 2a sub z. Okay, so P sub q as a vector should be equal to 2 divided by 9 times 2a sub x minus a sub y plus 2a sub z. Okay, so this is a vector projection of P along Q. Okay, let's go to part G and make sure we have done everything correct. So yes, should be like if we divide the result we had on the whiteboard, if we divide it by 9 and use the calculator, we would get this result. Okay, now we have this exercise, guys. We have this exercise. It has the same procedures that we followed in the previous example. So I leave it as an exercise for you. You do it at home. Okay. So you have two vectors. First, it asks for the asks you to find the component of vector E along F, and B, it asks for a unit vector that's perpendicular to both E and F. The final answers are there. You can just do it and compare your results with the key results here. Okay. Okay, we have this example here. I would stop at this point and we will do this example in the class, inshallah, on Monday. Okay. Until then, I hope you all have a good time and yeah, inshallah. Assalamu alaikum.